Okay, question 13.42. Consider the formation of a solution of aqueous potassium chloride. Write the thermochemical equation for the conversion of solid potassium chloride into its gaseous ions and the subsequent formation of the solution by hydration of the ions. Alright, so for a problem like this, we're going to start by writing the equation of the vaporization of potassium chloride, solid potassium chloride, into its gaseous ions. So it's going to look like this. The enthalpy for this reaction is going to be equal to the negative of the lattice energy, which is given to us in the problem. The lattice energy for potassium chloride is negative 715 kilojoules per mole, so the opposite of that would be positive 715 kilojoules per mole. Next step is to write out the equation converting the gaseous ions into aqueous ions, so we're going to go like this. And the enthalpy for that equation is going to be equal to the hydration energy, which is given in the problem as negative 686 kilojoules per mole. So to calculate the enthalpy of the whole solution, we're going to have to add these two together according, so these are going to cancel out since they're the same on both sides, so we're going to end up have potassium chloride solid giving us aqueous potassium ions and aqueous chlorine ions. And if we add the enthalpies together, we end up with 29 kilojoules per mole. And that is number 42. And go.
Chapter 13, review question 13.44. The solubility of methane, the chief component of natural gas in water at 20 degrees Celsius and 1 atm pressure is 0.025 grams per liter. What is the solubility in water at 1.5 atm and 20 degrees Celsius? For this question, we're going to want to use something called Henry's Law, which can be written one of two ways. We're going to want to address it using the C1 over P1 equals C2 over P2. And the C represents the concentration, and the concentration of a gas in a liquid at any given temperature is directly proportional to the partial pressure of the gas over the solution. So in this problem, the pressure given is 0.025 grams per liter. All right, and then what am I doing? All right, so anyways, so we're gonna work this. What we're trying to find here is C2. So we're gonna rework this, and we know that C2 is equal to C1 times P2 over P1. And like I just said, C1 is 0.025 grams per liter. So then P2 is going to be 1.5 atm, because that's the second pressure that they gave us. And P1 is at 1.0 atm. So, and this is equal to, again, C2. So we're gonna do this math right here, and we'll get an answer equal to 0.038 grams per liter. And that is the answer.
Alright, so this is number 15.46. It says if the solubility of a gas in water is 0.01 grams per liter at 25 degrees Celsius, with the partial pressure of the gas over the solution at 1 atm, predict the solubility of the gas at the same temperature but at double the pressure. So for this problem, we're going to use Henry's law again. That's C1 over P1 equals C2 over P2. First, we're just going to plug things in. It told us that we're looking for C2 again. The initial concentration is 0.010 grams per liter. The initial pressure was 1 atm. We're looking for C2, and it wants us to predict what happens if you double the pressure. So we're going to make that 2 atms. So one way to solve this is just to cross multiply. So 2 times 0.1 is going to be 0.020 grams per liter. And 1 times that is just going to be that. So we're going to end up with 0.020 grams per liter equal to the final concentration. So this shows us that when you double the pressure, you also, or when the pressure doubles, so does the concentration. So that is the answer.
13.48, what is the molality of NaCl in a solution that is 3 molar NaCl with a density of 1.07 grams per milliliter? All right, so let's just review really quick molality. Molality is going to be represented by the N, cursive N, I guess, sort of. And that is moles of solute over kilogram of solvent. All right. And in this case, our solute is going to be NaCl, and our solvent is going to be water. All right. So we want to find out what the mass of our solution and our NaCl. So to figure out, I guess, the grams of our solution, we're going to go 1 liter is, we're just going to do some dimensional analysis here. Milliliters all over 1 liter solution. They give us the density of 0.07 grams of solution over 1 milliliter solution. And that equals 1,070 grams of solution. And then we want to know, okay, so how many grams of NaCl are we working with? So they give us, we know we have 3 moles NaCl, and we know for mass is 58.45 grams NaCl, and 1 mole NaCl. And then, so when we do that multiplication right there, we get 175.4 grams NaCl. All right. So we know that the mass of the water in 1 liter solution must be the mass of the solution subtracting the grams of solute that we have. So simple subtraction here, 1,070 grams of solution minus or grams of solute, 175.4 grams, gives us the mass of the water, which is 895 grams water. All right, which is equivalent to 0.0895 kilograms water. All right, so again, molality, this all comes back to molality. Moles of solute divided by kilograms of solvent. So for the molality of this, it's going to be we're working with 3 moles NaCl divided by 0.0895 kilograms. And that is going to give us a molality, 3.35. Is the answer.
Okay, this is 13.50. Question is, what is the Molalla concentration of glucose, a sugar found in many fruits, in a solution made by dissolving 24 grams of glucose in 1 kilogram of water? What is the mole fraction of glucose in the solution? What is the mass percent of glucose in the solution? So this question is really 3 questions in disguise. It wants to know the molality, the mole fraction, and the mass percent of a solute in water. So we're going to focus on the molality first. Molality is moles per kilogram. Moles of solute per kilograms of solvent. It gave us our solute in grams, however, so we need to convert it from grams into moles. So what we're going to do for that is we're going to use some dimensional analysis and take 24 grams of glucose and use molar mass of glucose by adding up the atomic mass of all of its separate atoms using the periodic table. We got 180.16 grams of glucose for 1 mole. So after doing that multiplication, we get 0.133 moles of glucose. So now that we have it in moles, we just need to put it in to divide it over our kilograms of our solvent. So we're going to divide it by 1 kilogram of water, which is what it told us in the problem, was the solvent. So the molality ends up being 0.133 molal. So that's the molality. I'm gonna erase that now and move on to getting the mole fraction. So mole fraction is moles of the solute over the added number of moles of the different components in the solution. So we already know the moles of our glucose. We just calculated that to be 0.133. And we need to know moles of our components in our solution, which in this case is only glucose and water. So we know that we have 1 kilogram of water. We need to know how many moles that is. So we're going to take 1 kilogram of H2O and use some dimensional analysis to convert that into moles. End up getting 55.6 moles of H2O. So to get the mole fraction, we take the solute that we're getting the fraction of on the top. And we divide it over adding all of the separate components, so that's going to be our glucose moles plus our water moles. And when we do that, we end up with 0.0023. Not micrograms, that's actually moles. Well, actually, it's a fraction, so not units. Anyways, so that's the mole fraction. Moving right along. The last part of this problem asks for the mass percent. So mass percent is just like mole fraction, but you're going to use all masses instead of moles, and then you're going to times it by 100 to get a percentage. So we started out with 24 grams of solute. We started out with 24 grams of our solute, and then we're going to divide that by the total mass, which is, we want it to be all in the same unit. So since it was 1 kilogram, we know that it's 1,000 grams of water. And we're going to add that to our 24 grams to get our total mass of solution. And we're going to times that by 100 to get a percentage. So after we do all of that, we end up with 2.34% for the mass percent. And that is the end of that problem. Go.
All right, 13.52. A solution of ethanol in water has a concentration of 1.25 molality. Calculate the mass percent of ethanol. All right, so mass percent, again, is just going to be, mass percent is equal to the mass of ethanol divided by the total mass. Times 100%. Okay, so here we go. If we choose a solution that contains 1.25 ethanol alcohol, then we know that there'll be 1 kilogram will be the mass of the solvent. So 1.25 mole of ethanol is going to give us 1 kilogram of solvent, and we know this because of the molality given. All right, so let's just figure out how many grams of ethanol we have per grams of water. So grams of ethanol per grams of solvent, or solution, excuse me, solution. So they give us 1.25 molality, which we're going to use to say 1.25 moles of ethanol. And we know that that's going to be the equivalent of we know that we will have 1 kilogram of solvent, which is water. All right, and a little bit of dimensional analysis here. 1 mole of ethanol has 46.08 grams. Alright, and then 1 kilogram of water is equal to 1,000 grams of water. Alright, and if we multiply that across, we're going to get 57.6 grams of ethanol for 100 grams, excuse me, 1,000 grams of water. All right, so again, mass percent is going to be mass of ethanol over total mass of solution. So mass of ethanol, 57.6 grams, divided by 1,000 grams of water, total solution, plus 57.6 grams ethanol. Woo. All right, and do that math right there. And we're going to get, times 100% is going to give us 5.45% for the mass percent of ethanol.
Okay, talking about number 13.54. It says a solution of ammonia in water has a concentration of 7.5% by mass. It wants us to calculate the mole percent of ammonia in the solution, and then it asks us what is the Molalla concentration of the ammonia. So, what we know is that the concentration has 7.5% by mass. So we know the mass percent. So from this, we can assume that we have 7.5 grams of ammonia per 100 grams of solution. So the first thing that it wants us to get is the mole percent, which is different than the mass percent because it's in moles. So what we need to do is take what we know and convert it into moles. So we know we have 7.5 grams NH3. And if we use some dimensional analysis, we can convert that into moles by using the molar mass, which is 17. We end up with 0.44 moles of NH3. Now we need to know how many moles of water we have. So the way we can figure that out is first we need to know how many grams of water we have because this is grams of solution. And that's pretty simple to do because we know that we have 100 grams of total solution and there's only ammonium and water in the solution. So if we just take out the grams of ammonia from 100, just do some subtraction. 100 minus 7.5 gives us 92.5 grams left over, which is the water. So now we need to convert that to moles. So we can do 92.5 grams of H2O times mole of H2O over 18 grams of H2O. And we end up with 5.14 moles of H2O. So now that we know everything in moles, we can go ahead and get the mole percent. So percentages is part over total. So we want mole percent of ammonia, so we're going to take the part, which is 0.44 moles, over the total, so we're going to add them together. 44 moles of ammonia plus 5.14 moles of water. And then we're going to times it by 100 to get the mole percent. So after doing that calculation, you end up with 7.89%. That's your mole percent. but the question also wanted to know the Molalla concentration. So we've gone over Molalla already. It is moles per kilogram of solvent. So if we know the moles of our solute, 0.44, and we know that we were using 100 grams of solvent, so if we just convert that to kilograms, we can just quickly do 0.44 moles of solute over, we'll just convert this into kilograms really quick. It's going to give us 0.0925 kilograms of solvent. And when we do that, we end up with 4.76 molality. So that's our mole percent. That's our Molalla concentration.
13.56. Sodium nitrate is sometimes added to tobacco to improve its burning characteristics. An aqueous solution of sodium nitrate has a concentration of 0.363 molality. Its density is 1.0185 grams per milliliter. Calculate the molar concentration of sodium nitrate and the mass percent of sodium nitrate in the solution. What is the mole fraction of NaNO3 in the solution? Alright, so that we know that if we choose a solution that contains 1 kilogram of solvent, then it's also going to contain 0.363 moles of sodium nitrate. And we know that's assumed given the molality, which is provided in the question. So first of all, what we're going to want to do is we're going to convert number of moles of sodium nitrate to grams. So this is just going to be simple dimensional analysis using the molar concentration. So 0.363 moles of NaNO3 is going to be equal to, we know that it has 85 grams in 1 mole. And again, you can find 85 grams just by adding the molar mass of the compounds, so of the elements. So multiplying that across, we get 30.9 grams as the mass for the sodium nitrate. Alright, so now we're going to find the mass percent of the sodium nitrate, and that's just going to be mass percent sodium nitrate, the amount of sodium nitrate, the mass divided by the total solution, the mass of the total solution. So equals 30.9 grams NaNO3, and we're going to add 30.9 grams to 1 kilogram. We know that 1 kilogram is equal to 1,000 grams. So when we add 30.9 plus 1,000, we get 1,030.9 grams. Alright, so we're just going to multiply that times 100%, and we get 3% for the molar mass, the mass percent of the sodium nitrate. Alright, now we want to find the molar mass, the mass percent of the solvent, so which is the H2O. So we know that we have 1,000 grams, and the total is 0.9 grams, and so for that we get 97.0 molar mass percent of the solvent. Alright, and we want to know what is the excuse me, what is the molarity of the solution as well. So I'm going to erase this, keep these numbers in mind. So the molarity of the solution, which is moles per liter, you know that we were working with 0.363 moles sodium nitrate. And liters for the total solution, we have 1,300, and we'll just round grams solution. All right, and we're going to use the density as a conversion factor. The density is given in the solution in the problem. And they tell us that it's 1.0185 grams of solution in 1 milliliter. All right, we're just going to carry this dimensional analysis down to the next line. And we know that in 1,000 milliliters, we have 1 liter solution. All right, and so crossing out the units. We get 0.359 molarity of NaNO3, and that is the molar concentration.
Looking at number 13.58, which says, at 25 degrees Celsius, the vapor pressure of water is 23.8 torrs. What is the vapor pressure of a solution prepared by dissolving 65 grams of glucose in 150 grams of water? We're assuming that the solution is ideal. So for this problem, we are going to be using, eventually, Raoult's law, which is our pressure of the solution equals mole fraction of the solvent times the pressure for the solvent. So from what they give us, we can't use this yet because we don't know the mole fraction. But we can get the mole fraction using what they gave us. So first of all, we have to convert everything that they gave us was in grams, so we need to convert it into moles so that we can get the mole fraction. They gave us 150 grams. Maybe I won't use this marker. 150 grams. Can you see that or no? Okay, 150 grams of water. I don't like this marker. Red. Times. Oh, so we're going to convert that to moles. So 1 mole of water is equal to 2 grams of water. And that gives us 8.32 moles of water. We also need to convert our solute, which was the glucose. They get 65 grams of it, and we're going to multiply that by 1 mole. Glucose is equal to 180 grams. Glucose. And we end up with 0.361 moles of glucose. Okay, so now that we know the moles, we have everything in moles, we can get the mole fraction, so we can plug it into this equation. So our mole fraction is going to be, we need the mole fraction of the solvent, which is water. So we're going to put the solvent on top. So that's 8.32 moles of water. We're going to put that over the whole, which is going to be 8.32 water plus our moles of solute glucose. And when we do that, we get 0.957 as our mole fraction for our solvent, which is water. They also told us in the very beginning that at 25 degrees Celsius, the water had a partial pressure of, or vapor pressure, sorry, of 223.8 torrs, which is going to be this number. So now we have both of those and we can solve for that, which is what we want in the first place. So what we're going to do is plug that in to get so we get 0.957 our mole fraction times 23.8 torrs our vapor pressure, and we end up with 22.8 torrs for the total pressure of the solution. And that is number 58.
13.60. At 25 degrees Celsius, the vapor pressures of benzene and toluene are 93.4 and 26.9 torr, respectively. A solution made by mixing 35 grams of benzene and 65 grams of toluene is prepared. At what applied pressure in torr will this solution boil? All right, so again, this problem, similar to the last one, we're going to be dealing with Raoult's law. Which states the solution is equal to a fraction of the solvent times pressure of the solvent. All right, and so we want to know what the pressure of the benzene and the pressure of the toluene will be. So pressure of the benzene we know is going to equal X times the mole fraction of the benzene times the partial pressure of the benzene. And again, pressure of the toluene, which we'll just abbreviate there for T equals X of T times T, which again we got from Raoult's law. All right, so to begin with, we're going to be solving for the mole fractions of both the benzene and the toluene. So we want to find the moles of benzene. So in order to get that, they tell us that we are dealing with 35 grams of benzene, and we know that in 1 mole there is 78.11 grams. And that tells us, do the multiplication, we're going to end up with 44.8 moles of benzene. And then for the moles of toluene, they tell us that we're given 65 grams. We know that in 1 mole there is 92.14 grams of toluene. Multiplication tells us that there's 70.705 moles of toluene. T and B. All right, so using this, we're going to solve for the mole fraction. So here we go. X of benzene is going to be 0.448 moles divided by 0.448 moles plus 0.705 moles. Benzene and toluene make the total, and we're just interested in the mole fraction of the benzene. So when we do that, we get 0.389. And then when we do this for the tooling, it's going to be 0.705 moles all over 0.448 plus 0.705. And we have 0.611. All right, so we're going to plug these numbers into here to find the pressure of the benzene. So what we'll do is I'll just write this above here, 0.389 and 0.611. All right. So, partial pressure of the benzene, well, I'll just write it out again. Okay, so P of B, we know, is going to be 0.389 times the torr, the partial pressure which they gave us, was 93.4 torr. And so when we do that multiplication, we get 36.3 torr. And then the pressure for the tooling is going to be 0.611 times partial pressure, which is given 26.1 torr. You get 16.41 torr. All right. So all we have to do is add those up, and when we add that up, those two values, we get 52.7 torr. And that is the answer that we're looking for.
Alright, number 13.62. Benzene and toluene help achieve good engine performance from lead-free gasoline. At 40 degrees Celsius, the vapor pressure of benzene is 184 torr, and that of toluene is 58 torr. Suppose you wish to prepare a solution of these liquids that will have a total vapor pressure of 96 torr at 40 degrees Celsius. What must be the mole percent concentrations of each in the solution? Alright, so this is kind of a backward solution. It gives us everything we need to know. I'm just going to go ahead and write the things it gave us and then sort of organize. So we know that the benzene the benzene, which I'm actually just going to abbreviate to B, was 184 torr. We know that the toluene was 58 torr. And we know that what it's asking is what mole percents do we need of both to get a total of 96 torr. So what the equation that we need to use here is the same one we've been using. It's so the pressure of the total solution. It's a little bit of a variation on it, also incorporating a different law where we split them up and we add them together. So it's the mole fraction of benzene times the partial pressure of benzene added to the mole fraction of toluene times the partial pressure of toluene. So that's what we are going to be using. The only problem is that we don't know either of these, but we know all of the pressures. So what we do know is that these are fractions which added together create a whole. So we do know that added together they should equal 1. The mole fraction of benzene plus the mole fraction toluene is going to be equal to 1 because they're just ratios of each other in the total solution. So, since we know that this plus this is 1, we can manipulate that just using algebra to solve for one of them. In this case, I chose benzene. So we know that 1, actually I solved for toluene. We know that 1 minus the mole fraction of benzene is equal to the mole fraction of toluene. We can do that just using algebra. So now we know, now we can set everything. If we just substitute this in for that, we'll be left with only one variable, which will be our mole fraction for benzene. And once we have one variable, we can solve for it. So I'm just going to go ahead and start plugging things in. The total pressure was 96. X mole fraction of B is our unknown. The partial pressure of benzene was 184 torr. The mole fraction of toluene is what we just solved for over there, so it's 1 minus X of B. And the partial pressure of toluene was 58 torr. So now I'm just gonna start using some algebra to break this down. So we have 96 equals 184 X of B plus, and then factor that in there and you get 58 minus 58 X of B. So now, just using algebra, I'm going to combine these two terms since they're both terms of X, and then I'm going to take that from this side and from this side to eliminate it. So what I end up with is 38 equals 126 X of B. And if I divide both sides by 126, I get X of B equals 30. So if that's the mole fraction, so all I have to do with the mole fraction is times it by 100 to get the mole percent. So the mole percent is going to be 30% for benzene. And just by process of elimination, you have two things and they're both percentages, they add up to 100. So if you have 30% benzene in the solution, then you need 70% toluene. And those are the mole percents that you need to get 96 torr, which is what it asked. And that's the end of that problem. Thank you.